So we're happy to have Mikhail Cherdantsev with us today, who will talk about stochastic homogenization of high contrast media.
Okay, thank you, Jonathan. Thank you everyone for joining today's seminar. So this is the plan of the talk. First, I will give a very short introduction into homogenization, classical and no high contrast homogenization. Then I will speak quickly about periodic high contrast problem and about the bandgap spectrum. And then I will move on to stochastic high contrast homogenization. So we started this project quite a while ago now, and a couple of years ago we published a paper about stochastic high contrast homogenization. When I say we, I mean myself, Kirill Cherednichenko, and Igor Velcic. And that paper was about the bounded domain setting, and things in bounded domain setting were quite simple compared to what you have in the whole space setting. So the main focus of this talk is the whole space setting. Okay, so I will speak about bounded domain quickly about, I will give some results about the bounded domain. So in particular, convergence of the spectrum. Then I will talk about the properties of Zhik's beta function. And in the whole space setting, I will discuss what happens to the spectrum, to the limit of the spectrum of the high contrast operators. So as you can see from here, the limit of this spectra is not given by the spectrum of the homogenized operator. So, and we will discuss further how we can characterize the limit of the spectra, and I will talk about stochastically relevant and stochastically relevant parts of the spectrum of epsilon. Okay, so this is the introduction. This is the only three names. No, I'll give another name, but who dealt with homogenization basically goes back to as far back to Maxwell, Rayleigh, and Einstein. All three of them were working on heterogeneous problems and tried various heterogeneous problems and tried to obtain a problem with some effective coefficients which do not depend on the spatial variable. Okay, sorry. So now let us look at some basic periodic problem. We have an elliptic operator with periodic coefficients. We assume that these coefficients are uniformly elliptic. And let us look at this resolvent problem. When you pass to the limit, letting epsilon go to 0, you obtain this resolvent problem where the coefficients of the homogenized operator don't depend on x. And they're given by this well-known formula, which is called, so here, this term n, k, these terms are called character, and they solve so-called subproblem. This is all well known.
But you do not assume that epsilon is negative, do you?
No, of course not. I mean, sorry, it has to be, okay, epsilon is positive and goes to 0, so less than 1, right?
Okay.
Much less than 1, sorry, it's a typo. Okay, so now let us talk about stochastic homogenization. So, sorry, it's my mouse, it's the wheel on the mouse, it turns the slides too quickly. So first you need to understand the set a probability framework. So you have a probability space, and then you have a dynamical system Tx, and you use this dynamical system to cast the probability space into physical space and define random coefficients for the elliptic operator. You assume that the dynamical system is ergodic. Okay, these are some technicalities which I'm going to skip. One of the important properties of ergodicity of the dynamical system is that you can pass to the limit. So here, let me talk about the terms here. So we start with the function f, which is defined on the probability space. Now, when you fix omega and apply the dynamical system, you can think about this object here as a function of x. Now, if f is integrable in the probability space, then this object, which we call the realization, well, in particular here, when we when we have x over epsilon, we will call it epsilon realization. So this realization is also integrable, and you can pass to the limit in the integral, and this is what you get. A stronger result is that, which is also valid, is that you have, if your function is from LP, then there is, in general, then there is weak convergence for the epsilon realizations. Okay, and you can use, so basically using the dynamical system, you can define probabilistic gradient in the probabilities, acting on functions living in the probability space. And because of the way it is defined, we have this property that if you take the realization of the probabilistic gradient, you obtain the gradient of the realization. Maybe this is a typo here, so we need to apply Tx to omega. Sorry. Okay, so you can use this dynamical system in order to define these random coefficients here. So again, you take a realization of a function defined on the probability space. You replace y with x over epsilon to make the characteristic size of the heterogeneity small, and then you pass to the limit in this resolving problem. Everything else apart from the probabilistic setting is very similar to the periodic homogenization. You obtain the limit homogenized operator with constant coefficients. These coefficients are given by a very similar problem now, by a very similar formula. Now it is defined on the these characters here defined on the probability space, and they solve a very similar cell problem. Well, we call it, I still call it cell problem. Probably it's not an appropriate name for that, on the probability space. Okay, so in both in periodic and stochastic settings here, when you have uniformly elliptic coefficients, the spectrum of the limit operator is the whole positive half line, and there are no gaps in the spectrum of the limit operator. And you have Hausdorff convergence of the spectra of operators A epsilon to the spectrum of A home. Okay, so all the gaps disappear if they existed. Okay, let us look at the high contrast setting. So why high contrast is interesting is because in the limit you get a homogenized operator which has gaps in infinitely many gaps in its spectrum. Okay, so this was studied by sorry, I don't really see the title of my slide because it's blocked by Zoom panel. So this problem was considered by Zhikov initially in 2000 and 2004. So here is the setting. You have a periodically distributed inclusions, and you are so the lattice size is epsilon, and the inclusions are also for the epsilon, so they scale together with the lattice. You assume that coefficients inside the inclusions are for the epsilon squared, and outside are for the 1. Okay, again, you consider this, sorry. again, you consider the resolvent problem, you pass to the limit, you obtained homogenized operator. Now, this homogenized operator for the high contrast problem is of the two-scale nature. So this is the macroscopic component of the operator, which is defined, well, if you started from the whole space, it is defined in the whole space, and this is the microscopic component, which is defined on the inclusions, Q0, on a reference inclusion. Okay, so you can actually, if you are interested in the spectrum of this operator, you consider the formally the spectral problem, and you can decouple it. Right, so if you look at the microscopic part, you see that this term depends only on x. So let us go back slightly. So once again, so this macroscopic part, this is the equation on the function u0, which depends on x only. Now here in the microscopic equation, the unknown function v depends on variable y. You have derivatives with respect to y, and x plays the role of parameter, a parameter here. Okay, so once you get rid of f and you have the spectral problem, you can formally perform the separation of variables like that, and you see that the this function b here solves this model equation on the inclusion with Dirichlet boundary conditions. So function v equals to 0 outside the inclusion. Okay. Now, if you assume that lambda is not in the spectrum of the Dirichlet Laplacian on this inclusion, you can solve this equation, plug this v into this formula. So here is the angle brackets mean the integration with respect to y, right? And then you get this equation, macroscopic equation, when there is no term v, and this parameter function beta of lambda is given by this formula. So this is pretty straightforward, right? And what follows next, this infinite series, is the spectral decomposition of the solution B in terms of the eigenfunctions and eigenvalues of the Dirichlet Laplacian in the inclusion. Okay, now if this is the spectrum of the homogenized operator now, so it's all the points lambda such that beta of lambda is positive. Then you need to take the closure of this set, and additionally you need to add to the spectrum eigenvalues which correspond to zero mean eigenfunctions, eigenvalues of this Dirichlet Laplacian. If you look at this formula here, it's obvious that they are missing from this formula, because when you integrate with respect to y, these corresponding eigenfunctions, they just disappear from the sum. Okay, in the bounded domain setting, the only difference is that it's you take the points lambda such that beta of lambda belongs to the spectrum. If you look compared to this formula, to the spectrum of this macroscopic operator. Okay, just a second. Where am I? Okay, so this is the picture of this is the graph of beta of lambda. So it has these blow-ups at the points nu j, eigenvalues of the Dirichlet Laplacian. So it is the red intervals are in the spectrum of the homogenized operator, and then these red dots here, they are nu j primes. They are eigenvalues corresponding to zero mean eigenfunctions. So, and you have infinitely many gaps here in the spectrum. Okay, so this motivates the study of high contrast operators. Up until our recent work published in 2019, there was no any known at least we didn't know any study of high contrast stochastic problems in terms nobody studied operators and their spectra. Okay, so let us look at the high contrast stochastic setting. So probably I better to show a picture first. So there are two model examples I want you to think about when you think about high contrast stochastic problems. So you have, assume you have a periodic lattice in the whole space. You have a random distribution of inclusions inside the cells of this lattice. So you place an inclusion in each cell of the lattice with probability 1/2. And assume for simplicity that in this example, the inclusions have the same shape and size. Right. Another model example is that, again, you have a periodic lattice, and now you place an inclusion in each cell of the lattice, but you let the size of the inclusion, for example, you can take balls of radius r, the inclusions for, you can take for inclusions the balls of radius r, where r takes some value, takes values in some interval, right? And I is chosen randomly here. Okay, let us go back to the presentation. So this is the picture here. So you assume that, and then you just scale it by epsilon, the whole picture. Now you assume that in the inclusions, your coefficients are for the epsilon squared, and outside are for the 1. So this is the notation. S naught epsilon denotes the set of inclusions, and S1 epsilon is the complement to this set. We look at the same resolvent problem. Pass to the limit. In fact, passing to the limit in this setting is not much more difficult than in the periodic setting. So it's very straightforward, using more or less the same tools. Standard two-scale convergence, which is the standard tool in homogenization, is replaced with the stochastic two-scale convergence, but basically it's very similar notions. And so you obtain this homogenized operator, which, as in the periodic case, is of two-scale nature. So you have a macroscopic component of this operator and the microscopic component. So U naught here doesn't depend on Y, and V depends on, doesn't depend on omega. Omega is the an element of the probability set of the probability space. And here the microscopic equation is in terms of the probabilistic Laplacian, again with directly boundary conditions. Okay, you cannot, rigorously speaking, you cannot set define what the trace of a function in the probability space, but you just assume that your function v belongs to the space H1 on the whole omega and is 0 outside this set O. So what is this set O? This is basically the reference set that creates this randomly distributed inclusion. So let me go back again to the pictures. Sorry, just a second. To the picture that I have. So we have a probability space omega, and we choose a subset O. So how can we cast this setting into the physical space? We take, we fix omega, just an element of big omega, and we consider this set in Rn. So the set of all x such that if you apply the dynamical system Tx to omega, this belongs to the set O. So so practically, if you look at what happens here when you do this, you get this picture here. So O omega is exactly the collection of these randomly distributed inclusions. Okay, so we call this realization, as I already mentioned. So we can speak about the realization of a set, or we can speak about the realization of a function via the dynamical system. And once again, we use the term epsilon realization when we scale the spatial variable. Okay. So basically, this set O here is a kind of a reference inclusion in the probability space. Okay, I will skip these two examples. Basically, sorry, it's my mouse again. So they describe what I've shown you on the pictures. Okay, let us talk about the spectrum of the limit of the homogenized operator. So story here is exactly the same. You can look at the microscopic component of the spectral problem, perform the separation of the variables, and this B function solves the is the solution to the resolving problem for the Dirichlet Laplacian. Again, we substitute this back into the macroscopic equation and integrate with respect to omega, and we get this macroscopic spectral problem where beta of lambda is defined by this expression, which is absolutely analogous to what we have in the periodic case, with the only difference that you have omega here rather than the periodic unit cell. Okay, sorry, I will skip this. It's not very important. So very similar, very similar characterization of the spectrum. Well, a completely analogous characterization of the spectrum as in the periodic high contrast case. So let us move on. I'll just show you the pictures. So the difference, slight difference, comes from this random setting, right? So when you need to integrate with respect to in the probability space, so you in this simple example, when you have inclusions appearing with the probability 1/2 in the periodic lattice, so you take exactly the same. Let me go back slightly to the periodic setting. So you see this representation of the function beta of lambda here. So this is for the periodic setting. Now, what's the difference? So the difference in the stochastic setting is that you multiply that term here by the probability of an inclusion appearing in the cell of the periodic lattice. So basically, you have very similar function beta of lambda. It will be slightly squashed. So these intervals of the spectrum and the gaps, they will slightly, these edges will slightly, this end of each interval will slightly move, but everything else is very similar. Sorry, my mouse is somewhat uncontrollable. Okay, now if you think about the second example where you allow the size of the inclusions vary in some interval, you will have this picture. So basically, what happens is that if you fix one ball of one size and look at its eigenvalues and then start changing the size of the ball, the eigenvalues will move to the left or to the right depending on how you change the size of the ball. So basically, this spectrum you will have a union of spectra on these balls, which are here, these intervals, small intervals, this one, and this one, etc. And then, but the rest is pretty similar, right? So a function beta of lambda is not defined on these sets, which correspond to the eigenvalues of the balls, right? But where it is defined, it looks very similar to the periodic case. And in fact, this is true for...
Mikhail, in this formula at the top, you've got this dp brackets omega naught tilde equals r. Should that be something else, like omega naught tilde less than or equal to r?
No. No, it is equal to r. So basically, r is the parameter that takes values in this interval r1, r2.
I'm just thinking, what's the probability that omega naught tilde is equal to r? Surely it's 0.
No, but it's dp. It's the basically integration with the probability measure on that.
I see, sorry, yeah, I see, yeah.
On the set of the values of which r takes, right? But and in fact, this picture that you see here is rather general, and not rather general. This is what, if you have gaps in the spectrum of the probabilistic Laplacian, I will talk a bit about this later in more detail, you will have exactly the same picture for beta of lambda in absolutely abstract probability space. So this picture is valid not only for this particular example, but for the general, absolutely general setting. Okay, so let us speak more about the... Does anyone know how can I move the panel from the top, because it prevents me from seeing the titles of the slides? Okay, well, that's fine. I have it on the second screen. So, okay, so now we will talk about the properties of the probabilistic Laplacian and the beta function in the general setting, not just for the examples. So, and this is the new results that we. So what I talked about previously, it was published in our paper in 2018. Now the new results come now. So first result is that if you take, so let us talk about the notation first. So we denote each individual inclusion. So let me go back to the picture. So each individual inclusion here is denoted by O omega K. So O omega that you see here is a collection of such inclusions. So K is just the index. Okay, and then you take all eigenvalues, so by all eigenvalues corresponding to the Dirichlet Laplacian on this individual inclusion. So they are indexed by S. Here, omega is fixed. So let me go back to the picture again. So what does it mean omega is fixed? When we have a certain distribution of inclusions, random distribution inclusions, it means that we fixed omega and just work with this operator. So operator A epsilon is defined for a fixed omega, but then you can cast your dice once again, have a completely different distribution of inclusions. It will be a different operator, right? So when we fix omega, we speak about one particular distribution of inclusions. Now, if you take the union of this spectra over all inclusions K for that fixed omega and take the closure of this set. So this is what we denote by G to omega, calligraphic G. So you can prove that this set is constant for almost every omega. So moreover, it's this set is equal for almost every omega to the to the spectrum of the probabilistic Laplacian on the set O. Okay. So why is this, the first part of the statement is so important? So the second part of the statement was proven actually in our first paper, but the first part of the statement is new. So why is it important? It means that you can recover the spectrum of the probabilistic Laplacian, which from the first glance is completely abstract thing. And if you want to know it, you think, well, maybe I probably should know the all information about my probability space, omega. In fact, you don't need to know everything about omega or the probability space omega. You just need one typical, so those little omegas for which this holds, they are called typical. So you only need to know one distribution of inclusions, and from which you can reconstruct the spectrum of the probabilistic Laplacian on the whole space, on the whole probability space. Okay. Now let us talk about. Let me introduce some notation. So we will denote by K naught, O omega K naught, the inclusion that contains the origin. And we define this function. So for a fixed omega, you have an inclusion that is that contains the origin. So what happens? So how does it relate to all the rest of the inclusions in one particular sample, right? In one particular distribution. If you fix this omega and apply Tx, the dynamical system, to this omega, basically this just shifts your distribution by x. So you have one inclusion here, for example, and one inclusion here. When you apply when you apply Tx to omega, you just shift the whole thing like that by x. This is all it does. Okay, so now we look at this function b tilde, which for each particular omega is the solution of this resolvent problem for the Dirichlet Laplacian on the inclusion containing the origin. And then we define the function b of omega and lambda as the value of this b tilde at point y equals to 0, basically at this origin. So if you look carefully at what happens, if you take y so that this y lies in this inclusion here, belongs to this inclusion, and shift your omega by ty, the value of this function is exactly the value of the same b tilde of the same omega at point y. Okay, maybe it's difficult to follow right now because of the technicalities, but basically what I'm trying to do here is to reconstruct a function defined on the probability space from the functions defined in the physical space. This is what we are doing here. And we can do this in a nice measurable way. So let me go back to what we have here. Think about a function. So now you don't need to think about any. So A is not necessary defines coefficients, just any function. So you have the realization of this function in the physical space when you apply the dynamical system. For any function defined in the probability space, you have a nice measurable integrable if under certain assumptions function in the probability space via dynamical system. However, in general, if you take a function defined on the probability space, how can you go to, sorry, if you have a function defined on the physical space, how can you go to a function defined on the probability space? This is, in general, this is not possible. You need basically not just one function. You want to have a family of functions that depend on omega, and so that this is exactly f of t x omega, right? So this is called stationary family or stationary ensemble of functions f. So in general, it's a difficult question. So you can do this because these functions b tilde, they solve this exactly the same problem as you want b solve on the probability space. So they are counterparts of each other. Okay, so once you perform these constructions, which are very technical, in fact, you can prove that this function that we define is exactly the solution of the resolvent problem on the inclusion O. Okay. Also, you can prove that again, it's important to have this representation to prove that this the function beta, which is defined, let me see where it was defined, which is defined by this formula, is differentiable and its derivative is positive. This is how we know that we have this picture for our function beta of lambda in the absolutely in the general setting, and not just for some specific examples. One last remark: even though function beta of lambda is defined in the beginning as the via the integral of function b on the whole probability space, in fact, you don't need to know the whole probability space to recover beta of lambda. By using ergodic theorem and fixing a typical omega, you can integrate those functions, and when you average, well, as in the ergodic theorem, you get in the limit exactly the same. So you, in the limit, you recover the definition of beta of lambda. So you can recover the information about some objects in the whole defined in the probability space from one typical trajectory, exactly as in the first statement of the theorem at the top here. Okay, so what's next? So one can use some similar arguments. I don't want to go into details because there's a lot of notation, but we can construct the resolution of identity of the probabilistic Laplacian. And again, one can recover this resolution of identity from one typical trajectory, from one typical omega. When I say trajectory, I mean Tx omega for fixed omega. Okay, so here is another statement that we have about the microscopic operator and its relation to the spectrum of a home. We already know that the spectrum of the probabilistic Laplacian, this one, is a subset of the spectrum of a home. Now we can show that the point spectrum of a home is exactly the point spectrum of the probabilistic Laplacian whose elements have zero mean eigenfunctions. Okay, so this is the statement. And well, if you ask how the point spectrum of the how the corresponding eigenfunctions of the A home look like, well, you look at the spectral problem and then you realize that the first, if okay, what's I think one bit is missing. Ah, yeah. So if psi is the zero mean eigenfunction of the probabilistic Laplacian, then the eigenfunction of the A-home looks like this, right? You take arbitrary L2 function in Rn, and the first function here in this decomposition is just taken to be equal to 0. Okay. In the case when S is bounded, so let us speak about the convergence of the spectrum, of the spectra of A epsilon. So if you're in the bounded domain setting, you have Hausdorff convergence of the spectrum of A epsilon to the spectrum of A home. This is not really difficult to see, and so one bit of the convergence comes from the two-scale resolvent convergence of A epsilon to the A home. And property B, the second bit of the Hausdorff convergence can be proven directly, because when you're in the bounded domain setting, you have compactness of the eigenfunctions U epsilon. So and then you just pass to the limit. You only need to prove that this is not 0, and this is because you have compactness, it is true. So so this is how it's done. Now, what happens in the whole space setting? So the two-scale resolvent convergence still holds. It's exactly the same. The argument is exactly the same as in the bounded domain setting. So you have inclusion of the spectrum of A home into the limit of the spectrum of A epsilon. Okay. However, if you look at our simple examples, so in the first example, this one, so if you look at carefully at the setting and the assumptions here, you can see that we can find arbitrary large, for example, balls containing no inclusions at all with probability 1. So for almost every omega, the corresponding distribution of inclusions will be such that there will be arbitrary large balls or any sets containing no inclusions at all. It means that you can just do some standard constructions of Weyl-type sequences and show that every positive lambda is the point of the spectrum. So this is what we have here. And well, and obviously the limit of this set is the whole positive half line, and it doesn't coincide with the spectrum of A home. Now, if you take the second example where you let the size of the inclusions vary randomly, again, you still again the limit of the spectra does not coincide with the spectrum of A home. It's larger. So if you look at this set, which is the limit of the spectrum of A epsilon, it looks a bit similar to what how the spectrum of A home defined for this example, but in fact it's larger if you carefully look at it. So there we basically integrate with respect to R, and here we take the union for all possible values of R. Okay, so what happens here? As I already said, as in the first example, Weyl-type sequences for the points that belong to the spectrum of A epsilon and are outside of the spectrum of A home are captured in the non-typical areas. For example, as in the example 1, these are areas which contain no inclusions. Okay, so what can we do? How can we characterize the limit of the spectra? So I'll try to go quickly. There are some technical bits here, but I'll talk just about the main idea. So we take a sequence lambda epsilon from the spectra from the spectra of A epsilon that converge to some lambda. Okay, it means that there exists a Weyl type sequence which satisfies this condition with right hand side vanishing in the limit. Sorry, where am I now? Sorry. Now we split our whole space into the cubes of size L, and in each cube we consider what happens to that thing. And it's not difficult to see that you always confine the cube such that, so psi epsilon is that specific cube for which this is true, such that this holds with this, so this bound holds. And if you shift the cube to the origin, so we have a sequence of cubes for each epsilon, such that for each epsilon you have this, right? And this cube is shifted by psi epsilon here. Okay, we shift it to the origin so that we stay in the same set, right? And we normalize it. So U tilde here is, so it's a technical bit, it's the extension of U epsilon such that you control its gradient. It's part of the high contrast business. Okay, so when you do that, you see that this sequence of functions, they defined in the same cube. Well, it should be probably, well, never mind. So it's bounded from above and from below, it's L2 norm, and it solves this problem with a small right, so it has this bound, right? And because of this boundedness here, and you can also show that its gradient is bounded as well, you have weak convergence in W12 and strong convergence in L2. You have, so what we do here is we perform some compactification. Okay. So what's next? We want to pass to the limit, basically. Before passing to the limit, we need to introduce some notation. So we identify, so we assume that shapes, that the inclusions have, the shapes of inclusions can be parameterized by some parameter iota, right? And then we can also parameterize the solutions of the corresponding resolvent problems. And we also consider this characteristics function of each inclusion multiplied by the parameter multiplied by the parameter that parameterizes the shape of the inclusion. So this function is bounded in L infinity, and it converges in the sense of Young measures to some Young measure with this in this support. So basically the Young measure represents the volume density of the inclusions with the shape iota near point x in the limit. Okay, okay, so when you multiply, let us go slightly back, just sorry. So if you consider, sorry, this is something wrong with my mouse. If you consider that thing, that bound, you can write it as an equation with small right hand side here. So multiplying by a test function with the W epsilon tilde times the multiplied by a cutoff function, so that you can integrate by parts. Well, you integrate by parts, look carefully at what happens there, pass to the limit, and in the limit you see that you obtain this inequality where L is the size of the cube. Okay, so this bit here is positive, this goes to 0 if you let L go to infinity. Hence, we conclude that this guy here is positive. So this gives us condition on the point lambda, which is the limit of the sequence lambda epsilon. And this is the theorem that we have. Okay, so we need, so basically the limit of the spectra is contained in the set G theta naught, which is the union of G1 theta naught and G2. G2 is basically the spectrum, the notation for the spectrum of the probabilistic Laplacian. And G1 theta naught is defined like this. So again, you see here some sort of beta function So this is a beta function corresponding to an inclusion of the shape of the shape parameterized by iota, and theta naught here is some minimal density in a sense of the inclusions around the point x. Okay, you can alternatively you can write this set like that, but I don't have time now, so can I have another, say, 5 minutes or so?
Sure, yes.
Okay, so maybe I still have time for that. So in fact, this is the way we define the set G1 theta naught in our paper. It's quite the same, it's just different notation. And here you consider only the shapes in one particular sample of the distribution of inclusions, right? And then you need to take the closure of this set. Okay, it means that you can recover this set from one typical omega and one typical trajectory Tx omega. Okay. Can we say something? So we basically have the lower bound on the limit of the spectrum. Can we say something about the inverse statement holds? At the moment, we can prove that the equality for some explicit examples, like those that I referred to throughout this talk. Also, we have an idea how to prove this equality under an additional assumption that we can do. I think we can do this. We think we can do this if we assume that the distribution of inclusions has finite range correlation, or the correlation decays very quickly. So it means that if you take two sets, so if you take a sample so if you take the distribution of inclusion, fix it, and you take two sets that lie sufficiently far from each other, the distribution in one set is completely independent from the distribution in another set. This is what finite range correlations mean. Okay, so and now I'm coming to the end of my talk. This is the last bit. I want to talk about statistically relevant limiting spectrum, or asymptotically approximate statistically relevant spectrum. So this is an idea that stems from the fact that if you look at this extra spectrum that is not contained in the spectrum of the limit homogenized operator, the corresponding Weyl sequences are supported on non-typical areas with some strange distribution of inclusions, non-typical distribution of inclusions. But if you think about this carefully, these areas lie far, far away from the origin. And when you want to construct functions that solve the spectral problem more and more precisely with smaller and smaller error, you have to find bigger and bigger sets with non-typical distribution of inclusions, and hence you have to move further and further away from the origin, so fast that basically it's not important for the practical problem if you stay somewhere if you're interested in what happens in a rather bounded in some bounded area of space, right, around the origin. So this is why we say it's that the spectrum that corresponds to such bad non-typical distribution of inclusions is statistically not relevant or physically not relevant, and we call the rest of this spectrum statistically relevant. So this is the idea, but I'll need maybe 3 more minutes to finish this. So, and this is the rigorous definition. So we assume that, so we say that lambda belongs to statistically relevant limiting spectrum of a epsilon, and we denote this set by SR, limit of sigma of a epsilon, if there exists a positive constant in the function g such that g satisfies this condition. So it's function of epsilon and L, epsilon go, and this double limit equals to 0, such that for each L there exists a sequence UL epsilon of functions that solve the spectral problem approximately, so some kind of whale-type sequence with the error that is controlled by this function g, and that it doesn't run away to infinity, so it doesn't disappear from the cube that is centered at the origin, right? So there is energy that stays inside this cube. Okay, and what we can prove is that the statistically relevant limiting spectrum of A epsilon is a subset of A hom, and the proof of this is rather simple. So it's basically the whole idea is in these several lines. I don't want to, so basically you just pass to the limit, you get UL, which is the wild type sequence for A hom, and the right hand side FL goes to 0 as L goes to infinity, and hence you conclude that lambda is in the spectrum of A hom. Okay, we also can prove the opposite statement, the reverse inclusion, which is technically more complicated, much more complicated, and the consequence, and this is proved in the absolutely abstract general setting, right? Not just for some examples. So, and as the corollary of these two theorems, we have the equality. Okay, I'll skip the proof, but it more or less goes along the lines of constructing an approximate eigenfunctions and looking at the error term. So here, error term is this ugly beast here, which involves some homogenization character in the stochastics, 3 homogenization characters in the stochastic setting. The important thing is that this error term satisfies this condition that we have in the definition of statistically relevant limiting spectrum. So basically taking, here lambda, if you take a point lambda in the spectrum of A hom, you can prove that it belongs to the statistically relevant limiting spectrum with function g replaced by this error term r. Okay. And this is the last slide. Which I called approximate statistically relevant spectrum. We don't really have the name for this guy here. So basically, what I just talked about was about the limit points of the spectrum of A epsilon, right? Now I want to look at this spectrum of A epsilon for fixed epsilon and try to separate statistically relevant bit from statistically relevant. Idea is the same. You need to have whale type sequence with some error term, which is exactly as in the proof of the previous statement, right? And now we can prove that this guy here, this is the subset of the spectrum of A epsilon, converges in the sense of Hausdorff to the spectrum of the operator A hom, which is equal to the statistically relevant limiting spectrum of A epsilon. Okay, so, and this is it. Thank you very much for your attention. Okay, I will stop share the screen now.
Are there any questions?
So I've got a question. So you mentioned at one point constructing approximate eigenfunctions, and that makes me think that the chances of generalizing any of this beyond the self-adjoint case must be a little bit slim. Is that correct? Or
yeah, well, I suppose so, because well, this essentially, so this is some standard stuff when you construct approximate eigenfunctions. You take just harmonic function that solves exponential harmonic function that solves the formally solves the equation, right? And then you modify it slightly so that it actually fits into the high contrast setting, stochastic high contrast setting. And the main thing is that once you know that your approximate solution solves this equation with a small error, you know that the spectrum is not that far, right? The spectrum is the distance to the spectrum is actually is bounded by this error term, right? But by the and this obviously there is nothing like that in the non-self-adjoint case.
Thanks.
Any other questions?
Yes, I had a question which might, I mean, it might be a bit naive because I don't know exactly the methods that you've been using to do this, apart from what you told us about today. But how important is it to your setting that the inclusions are identically distributed in every cell, or could there be a spatial dependence on the distribution of the inclusions?
So basically, we don't have any assumptions. So everything that I've talked about today is valid, apart from one particular statement. Let me go back to where it is. Where it was. So apart from this statement here, everything else is valid in the absolutely general abstract probability, or absolutely general abstract probability space. So so there could be correlations between the distributions of inclusions and so on and so forth. This is not forbidden. The essential assumptions that we make about the probability space is rather in terms of, well, you have some technical assumptions that certain measurability properties are satisfied, but they are rather natural. And the only essential assumption is the possibility of extending of the function from outside the inclusion inside, so that you control the gradients. And it means that the inclusions shouldn't come to each other too closely. So if you assume that there is a minimal distance between any two inclusions, then the extension property is met.
Okay, I see. I mean, so you could understand, for example, settings where the inclusions. So, for example, where there's the probability that inclusions. If you go to your example 1, where you had probability 1/2 that there is or there is not an inclusion in a given cell, you could, for example, deal with the setting where as you go away from the origin, the probability of there being an inclusion goes to 0, for example.
Say it again. What if you go away?
As you get further and further from the origin, the probability of there being an inclusion in a given cell goes to 0, for example.
No. This would be against the ergodicity assumption. So we assume that the whole thing is ergodic. It means that if you take a certain distribution of inclusions and just decide to shift it by some large vector, so that you pull it from far away to the origin, the distribution of the inclusions is the same in the limit. Well, if you let epsilon go to 0.
Okay, so you still need at least
this ergodicity is really so the ergodicity assumption is the paramount. This is the first thing, but you always assume this not only in high contrast homogenization stochastic thing, but also in just standard classical stochastic homogenization. You always need ergodicity.
All right, thanks.
But for example, we can have so as an example, you can take random parking model. So when you park your inclusions quite densely so that there are no big gaps, right?
Mm-hmm.
So this is a nice example of some very relevant to applications, right? So you don't allow big chunks of space containing no inclusions, right? So everywhere is a certain, but actually you still have, even in this example, you still have these non-typical areas with non-typical distribution of inclusions. So if you can imagine that you can distribute the balls more or less densely, right? If you take the least dense distribution, you have dense, and it affects local beta function if you wish. And if you take very dense distribution, most dense, you have another local beta function. This all affects the spectrum.
Any other questions?
Okay, how can I stop sharing this screen? Because when I press it, new share, how do I? I don't see it here.
Here, I can stop it. So if there are no other questions, let's thank Mikhail again.